This topic is redistribution of charges. Now, what is redistribution of charge? So let's consider that you have two isolated spherical capacitors, isolated spherical conductors, and they were isolated in the beginning. So let's consider that they were not connected here as shown in the diagram. Let's consider that they were like this, two spherical conductors, and they have individual capacitance as C1 and C2. They also have some charge within them, Q1 and Q2. So they will also have some potential, that is V1 and V2. Okay. So C1, C2, V1, V2, Q1, Q2, they have individual capacitance, charges, and potential on them. Now, if you join them, if you join these two by some conducting wire means that some charge can flow from this first one to the second one, or the second to the first. Now you see, because you have connected them and they have different potential, you know that the charges would flow from a higher potential to lower potential, you know that. So these two potential V1 and V2 here, might be V2 is higher than V1, then some charge from this to going to flow here, or maybe V1 is higher than V2, so some charge is going to flow the other side. So what you see, that there can be a redistribution of charge. This redistribution of charge would happen because both these capacitors have different potentials. Now, originally these two capacitors has a charge of Q1 and Q2. You can see Q1 and Q2. But after redistribution, that means after some charge from here to here or here to here, there would be new charge on these capacitors. That means after the redistribution of charge has happened, some new charge, that is the charge on the first capacitor, is also going to change, and the second one would also going to change. So this is what we have to understand, that what happens when this redistribution of the charge takes place, and what will be the new charge on these capacitors. Why new charge? Because some charge distribution have taken place. Now to calculate that, we need to calculate first a common potential. Why? What is a common potential? See, these two capacitors were initially isolated and separated, so they had individual voltage and individual potential. But now, because they are a part of same system, eventually they are going to have some potential, which is the common potential. Both of them will have same potential. So we need to first calculate what is this common potential. That is the potential after they are connected. Okay. Now to calculate that, we first need to find the total capacitance. Okay. We need to find the total capacitance and the total charge. Now, we know that the total charge would be Q1 plus Q2. Why Q1 plus Q2? Because these two capacitors are isolated. They are isolated and they are insulated also. So they don't lose charge to anything else. The total charge of the system Q1 plus Q2, that is going to remain same. Understand this very carefully. The Q1 plus Q2 is going to remain same. Some redistribution is going to happen. Some redistribution is going to happen where some charge from this to this flows, or this to this flows, but there is no new charge coming from outside, or there is no charge which is lost outside. So the total charge here will remain Q1 plus Q2. What will happen to the capacitance? Now, we first have to understand the capacitance of the whole system. This is our whole system. The capacitance of the whole system will be C1 plus C2. C1 plus C2. See why C1 plus C2. First, we are considering that this conducting wire has no capacitance. Okay, it does not have any capacitance. We are assuming it. Okay, so if the capacitance of the thin conducting wire is negligible, so first we are assuming that the capacitance of this thin wire is negligible, and then we are also assuming that these two conductors are at sufficient distance apart so that they do not exert mutual electric force. Now, when we did capacitance as a property of a conductor, then we understood that the capacitance of a capacitor C is affected by other conductor nearby. I hope you remember that. Okay, other conductor. So we are assuming that these two capacitance C1 and C2 does not change. The C1 remains C1, the C2 remains C2, and they do not change because of each other. Next, if you think this is general misconception, if you think that this is a series, visually it may seems to you that this is a series and this is a parallel. Most student would find that this is series capacitors and this is parallel capacitors, but this is not so. Neither this is series nor this is parallel, because series and parallel of capacitors are always with respect to an initial and an external potential difference. The capacitor C1 and C2 can be in series only with respect to this potential source. This two can be parallel only with respect to the potential source. If there is no potential source, then both of them are not series or not parallel. They are not series or parallel. If you just extend this wire, this particular conductor, this capacitor can be stretched and made here. Then it will look like this. So this type of setup where there is no external potential source, would not qualify as a series or a parallel circuit. Okay. So here also we see that there is no external potential source. There are only two conductors and they are connected. So in that case, the total capacitance will be C1 plus C2. The total capacitance will be C1 plus C2. This is not because that they are parallel, not because they are parallel. Okay, not because they are parallel. Understand this, they are not because C1 and C2 is not because they are parallel. It's just their capacitance will add up when there is no external potential source. So now the common potential of both of this will be is equal to the total charge. We have understood what the total charge is. That is Q1 plus Q2, as no charge is getting lost or no other charge from external sources coming to the system. And the total capacitance is C1 plus C2. So your common potential will become what? Q1 plus Q2 divided by C1 plus C2. Now Q1 is the charge on the first capacitor initially when this was not connected. So you can also write that Q1 is equal to C1 V1 and Q2 is equal to C2 V2. This is the initial values of Q1 and Q2 before it was connected. So then your Q1 plus Q2, this value can be written as C1 V1 plus C2 V2 over C1 plus C2. Now, as you have found out this common potential, common potential you have found out. So let us find the new charge. New charge means, as we have discussed before, some redistribution of charge is going to happen. And after the redistribution has happened, after the redistribution of charge on A and B, there is Q1 and Q2 will change. That is some new charge will come. The charge on the capacitor will change, and the charge will change to what? See, the capacitance, that is C1 and C2, these are constant. You know that capacitance is constant. So the capacitance does not change. The charges would change because now these two capacitors have different potential. Initially, they were having Q1 is equal to C1 V1 because the first one had the potential of V1, the second one had the potential of V2. But now both of them has the same potential V. So the new charges upon them will become what? C1V, and this V is the common potential, and C2V, and again this V is the common potential. If you divide these two quantities, you can get the ratio of the charge. That is Q1 dash. Q1 dash is a new charge on the first capacitor. Q2 dash, new charge on the second capacitor, will be in the ratio of C1 by C2. That is the ratio of their capacitance. Now you already know that the capacitance of a spherical capacitor is 4 pi epsilon naught R1 for C1 capacitor and 4 pi epsilon naught R2 for C2 capacitor. You can take this 4 pi epsilon naught out, and this then will become R1 by R2. So you see the new charge on these capacitor will be in the ratio of their capacitance and also in the ratio of their radius. Okay, a ratio of their radius. Now, after this redistribution of charge has happened, there will be new charge on the capacitors and a common potential. That means it will have some different energy. The system energy will be different. So we need to find the loss of energy in redistribution. Loss of energy in the redistribution. So initially both these conductors or capacitors have Q1 charge, C1 capacitance, V1 potential, Q2 charge, C2 capacitance, V2 potential, and they had energy as half of C1 V1 square and half of C2 V2 square. This was the initial condition. Okay, this was the initial condition. That means a condition before they were connected. So the initial potential is half, initial energy, total energy is half of C1 V1 square plus half of C2 V2 square. But now because they are connected, as a system, they will have a different energy. What would be that energy? That energy will be half of C1 plus C2, because now their total capacitance is how much? Their total capacitance is C1 plus C2. We have understood that. And common potential, they have common potential. The potential of both of them is same because they are a part of the same system. This common potential square. So this will become how much? Half of C1, C2, and common potential you have just found out here. You see, you have found out here this common potential. That is C1 V1 plus C2 V2 by C1 plus C2. So we are going to put it here. C1 V1 plus C2 V2 divided by C1 plus C2 and whole square. So this is our final potential energy. Final potential energy of these two conductors. And this is our initial potential energy. Now there will be a difference between the final and the initial potential energy. There will be a difference, and you can subtract the initial and final. Okay, you can subtract the initial. So this is your initial potential energy, half C1 V1 square plus half C2 V2 square. And this is your final potential energy, that is C1, half of C1 V1 plus C2 V2 whole square. The difference of these two will come to this. You can do this derivation. This is not a standard derivation for PU. So this will be the difference. Difference means that the initial energy will be more than the final energy. You see, this value is basically positive. This is a positive value that you are getting here. That means this value, initial energy, is more than the final energy. Now, why the initial is more than final? Or if initial is more than final, that means there has been some loss in the energy. And why there is a loss in the energy? The loss in the energy is because if the charges are going to flow, think like this, if the charges are going to flow from potential V1 to V2, let's say Q charge flows, we know that in this process some work will be done. In this process some work will be done, and because some work will be done, some energy will be lost. Energy will be lost. So when two charge conductor are connected, the charges flow from the higher to the lower potential side till the potential of the two conductors get equalized. In doing so, there is always some loss of potential energy in the form of heat due to the flow of the charges in the connecting wire. So when we do this redistribution of charge between two conductors, there will always be some loss of energy. Okay, there will always be some loss of potential energy in the form of heat due to the flow of the charge in the connecting wire. Next topic is effect of dielectric on various parameters of capacitor. So various parameters of capacitor. So let's say we have a capacitor. Okay, we have a capacitor which is not connected to anything. Not connected to anything means it is isolated. Okay, not connected to anything means it is isolated. And what would be the parameters of this capacitor? So what is a parameter? Parameter means what is its charge, Q naught, the initial value. What is the capacitance of this capacitor, C naught? Then what is the potential of this capacitor, V naught? Similarly, electric field, E naught, and energy. So we are going to understand that what happens to these five parameter. What happens to these five parameter when a dielectric is inserted between the plate. If I insert a dielectric between the plate of the dielectric constant K, then these five parameters will change. Okay, there will some change happening to this five: charge, capacitance, potential, electric field, and energy. Some change will happen, and we have to understand what the change is going to happen. Now, first understand the meaning of isolated very carefully. This is the key to this whole concept. Isolated means that this capacitor, if you give some charge Q naught to the capacitor, Q naught, then that Q naught charge is going to stay with it. It is not going to be lost. It is not going to be lost. Or no other charge is going to come to the capacitor also. Why? It is isolated. That means it is not connected to any cell. It is not connected to any cell. It is not going to get any charge from the cell or any other object or any other entity. It is completely isolated. So in an isolated condition, the charge Q naught remains same or constant. The Q naught value will not change. Okay, this is not going to change. And why not going to change? Because this is isolated. It is disconnected from the cell. Okay, the battery is kept disconnected from the capacitor, isolated capacitor. So our initial values of charge is Q naught here, which is C naught, B naught. Then initial electric field will be V naught by T. Initial energy will be half C naught B naught square, and so on. Now let us find what happens to the parameters when a dielectric is inserted. when a dielectric is inserted. Now you already know that when a dielectric is inserted in a capacitance, if you have a capacitor, and if you insert a dielectric in a capacitor, okay, if you insert in a dielectric in the capacitor, then what would happen to the capacitance? So the new capacitance will become the K times of the original capacitance. This you already know. Okay, this you already know. If I insert a dielectric of capacitance K, that capacitance will, if I capacitance value will increase. Now, just now we discussed that the charge remains the same. That means the Q naught charge now still remains the same. But previously Q naught value was C naught V naught. But now because you have inserted a dielectric, the capacitance value will become K times C naught. Now, as because this is same, that means your potential must decrease by K times. So as these two K cancels, and again it will become C naught V naught. So as we discussed the charge, because the charge remains same and capacitance increase by the value of K, that means the potential must decrease by the same value K, so that your charge still remains C naught V naught. So what we understood, that the Q naught charge remains the same, this remains same, and capacitance value will increase K times, potential value, the new potential value will decrease by K times. As electric field is proportional to potential, so electric field value will also decrease by K times. And energy, the new energy will be half of the new capacitance and the new potential square, half of CV square. So new capacitance has become how much? Half of K times the old capacitance, and the potential, new potential has become 1 by K times the old potential square. So you will end up in having this as half of, so this will become this square, V naught square, K square, this K and this 2 cancel. So you will eventually get half of C naught V naught square, but 1 K is still there, so it will become 1 by K. So you can say that the new energy will be 1 by K times the original energy. So this is what happens to the 5 parameters. The charge remains same, that does not change. You have inserted a capacitance, so if I've inserted a dielectric between the plate of the capacitor, so capacitance value will increase by K, potential value will proportionately decrease by K, electric field because proportional to potential, so that will also decrease by K, and the new energy will be 1 by K times the original energy. But this is all going to happen only in the condition of a isolated capacitor, when it is not connected to any battery, disconnected to the battery. Only in that case this kind of change is going to happen. Now let us find out what kind of change is going to happen when it is connected to the cell. So next topic is that what will be the effect of these parameters when they are connected to the cell. So when the battery remains connected across the capacitor. So if the capacitor's plate are connected to the battery or the cell, then the potential difference across the capacitor will always be same as that of cell. If the cell has a potential of V, then the capacitance will also always have a potential of V, because it is connected to the same potential difference of the cell. the charge in this case, the charge Q naught in this case may change. It may change. And why it may change? Because the capacitor is connected to the cell, and the cell is a kind of a reservoir of charge. Huge amount of charge is there in cell. So the cell can provide any amount of charge to the capacitor whenever required. Not like the isolated case where the capacitor was not connected to anything. Here, the capacitor is connected to the cell. So charge can be provided to the capacitor anytime. That means the charge Q naught value is going to change. But potential value will remain same. Okay. So charge may change and potential remains same. Now, if the potential remains same, then what will happen to other values? So the new charge, because if you insert a dielectric here, and this dielectric constant is K. So this you already know that if we insert a dielectric, then capacitance will change, and the capacitance now will become K times the old capacitance. After inserting the dielectric, this will be my value of the capacitance. Potential remains same. We have discussed this. So what will be the new charge? The new charge will be the new potential, new capacitance times the potential. Now you can call it new potential or old potential, that doesn't change. So the charge will become K times the old capacitance value, that is this value here. Okay, this one K times C naught will become Cn, and this V. So you can very well see that the charge is going to increase K times C naught V naught. Charge is going to increase K times. Potential remains same. Capacitance increase by K, and charge is equal to C naught V naught, and that's how it will become K times C naught V naught. After inserting dielectric, charge will increase. Then what would happen to electric field? Electric field is proportional. Electric field is proportional to the potential. So electric field also remains same. And what will happen to energy? So new energy will be half of the new capacitance times the potential. And the potential has not changed. That is the same value. Only the capacitance has increased. So it will become half of K times C naught, and then V naught square. That means the energy will become K times the original energy. This is your original energy, this value here. Okay, this value here is your original energy. Okay, other than K naught. So it will simply become K naught times old energy. But again, all this changes is only going to happen when the battery remains connected across the capacitor. So be very, very careful in identifying whenever you are solving any kind of numerical which involves a dielectric being inserted. Any numerical you do where dielectric is inserted into the capacitor, first check it is connected to cell or not. If it is connected to the cell, then different changes is going to happen, as we have discussed here. If not connected to cell, then these kind of change is going to happen. So before solving any such numerical involving dielectrics and capacitor, first make sure to know whether the dielectric is isolated or connected to the cell.